Hello everyone, Michael Frank here again, and this is part 2 of the lecture on fundamental physics of reversible computing for day 1 of the CCC workshop. We're going to start this part of the lecture just trying to clear up some basic misconceptions about Landauer principle that unfortunately have been somewhat widespread in the literature. A lot of authors try to identify Landauer's principle with what I call the fundamental theorem of the thermodynamics of computing, which is basically just the observation that computational entropy is part of the total physical entropy. And depending on where we draw the boundary between our computational states, that entropy can move back and forth between part of the computational state or part of the non-computational state. And you can even do this physically by, say, raising or lowering a barrier between two degenerate states or sets of states. And that's all well and good, but simply moving entropy between the two forms does not necessarily increase total entropy. And some authors have pointed this out and used it as a critique of Landauer. Well, I would argue they're actually missing the whole point of Landauer's principle, which is that it is talking about not just movement of entropy, real entropy from computational to non-computational forms, but it's talking about erasure of computed information. And this is critical because information that has been computed holds correlations with information in other parts of the system. Meaning there's mutual information between those subsystems. And it's when you move that correlated information into a thermal environment, you will then lose the correlation information, and the total entropy will increase as you lose track of those correlations. All right, so there is an absolute entropy increase in Landauer's principle, and it's inherently associated with the fact that the information that's being erased is not just random information, it is computed information and has known correlations. So let's make this observation a little bit more formal, and I'll just start by pointing at this illustration, which is just a very simple case where we have a computer system that can be divided into two 1-bit subsystems, and the shading here is indicating probabilities and of the physical states making up the computational state. And in this example, we have that the bit y is a copy of bit x. Y is 0 if x is 0, y is 1 if x is 1. And this is a very common thing, right? You could copy one bit to another, or you could have a more complicated function with a larger number of bits. But the fact is that this is not a uniform probability distribution. This joint distribution has structure associated with these correlations. And if you were to just look at these bits in isolation and compute a reduced entropy for one of the subsystems, such as y, you would think, oh, y contains a bit of entropy. It's 50% chance of being in each of these in 0 or 1 conditions here. And you would think, oh, therefore I can move that entropy to the environment and move it back and I haven't lost anything. Well, that's not true, because if, let's say, you remove the barrier between these two sets of states and merge them into one, very briefly there's no change in the entropy, but this system will very quickly thermalize, right? If these states are sort of free to intermingle, and you very quickly get a uniform distribution over the microstates corresponding to that macrostate. And there's an absolute entropy increase when that happens. You've lost the correlations that you once had between the two bits. And you notice you can't undo this, right? If you try to raise the barrier again, you get back a state where the entropy of y is 50% like it was before, but the correlations would have been lost, if you just put the barrier back in. So this is what I think a lot of the authors who talk about Landauer are missing. They're sort of neglecting the degree to which correlations are central to what we do anytime we're doing deterministic computation, we're building correlations. And, you know, I'm not going to go through all of the steps of the formal argument to save time, but, you know, I just want to point out, if you define the independent entropy of a subsystem in a natural way, it's the same thing as the conditional entropy of that system conditioned on another one. And conditional entropy of a system that has been deterministically computed from another one is always zero. That's what it means to deterministically compute a result, is that that result is now completely determined by the input, right? So, so anytime, shot is that anytime you erase what you think is entropy in a subsystem and it's actually mutual information with another subsystem, the stuff that you thought was entropy, which was not really independent entropy, it ends up getting transformed into actual entropy, and entropy increases by the amount of that. Okay, so I think that's the conceptual nub of Landauer's principle that a lot of authors have simply missed. But I think once you see this, it becomes quite clear that Landauer was perfectly correct when you're talking about computed bits that contain known information or correlated information. There is an entropy increase associated from expelling those to the environment and letting them thermalize. Okay, so to me, this is kind of very undeniable and very obvious once you see the conceptual basis here. Okay, so now let's talk about reversible computing theory. Now that we understand Landauer, you know, the traditional theory of reversible computing is based on ensuring that we're only performing operations that never merge state and therefore never eject entropy into the environment. And so we have things like Toffoli gates and Fredkin gates and other simple reversible gates that perform one-to-one transformations of the computational states. Well, that's all well and good, but it's really just a special case of a larger set of reversible operations, which I call the conditionally reversible operations. And these are operations that perform a one-to-one map on the set of computational states that have non-zero probability in a particular physical operating context. And what I mean by that is, you know, when you design the architecture of a system, you can very easily arrange things so that certain constraints are always met by the state of the system. So it's always in a subset of the full state space. And as long as you are reversibly transforming the states in that subset, you can do that with zero necessary expulsion of entropy, of apparent entropy to the environment, and zero entropy increase required by Landauer's principle. So it's really just recognizing that you know, what we're trying to do in this traditional paradigm for reversible computing is really stronger than necessary, and that, you know, it's perfectly acceptable to build a computer out of primitives like this that are reversible when some precondition is satisfied, you know, as long as the design of your system ensures that indeed those preconditions are satisfied. And so this is what we're doing when we're building adiabatic circuits, actually, is we're using primitives in this more general class. And because it's a broader class of primitives, designs in general will be simpler if you build them from this larger class of primitives than they would be if you were constrained to only using this smaller set of primitives. And that's because these primitives in the smaller set are more difficult to implement. They're more complicated to build physically than some of the ones in this larger class that are still universal. All right, so again, you know, I don't have time to go into the details, but there's a paper, link to a paper there that you can look at. I don't have time to go through the next few slides in much detail, but basically the point of these slides is to basically describe in a quantum physics perspective what it means to implement a classical reversible operation. And, I wish I had more time for this, but the end of this, we're assuming there's some unitary transformation that applies to the model universe. And all of the stuff that's happening within the computer, as well as everything else in the model universe, is encompassed by that unitary transformation representing the physics of that system. We can also describe a closed system variant of this, where we kind of neglect the interaction between the computer system and the environment. And it's easy to see that this is fine because, you could always draw the boundary around the system far enough out that basically, having that be a closed boundary has no impact on the actual practical operation of the computer, right? So, eventually things may break down if you have too much heat building up in that system, but you could keep running fine for a long time. So there's nothing fundamental about the physics of a computer that has changed when you have a closed boundary around it versus an open boundary. So this is really just a technical convenience that lets us describe things in terms of unitary dynamics operating on the computer system itself. So it just sort of simplifies our description of the system a bit. There's some more technicalities here having to do with, accounting for the change in the computational basis over time, but they're not that important to the high-level points I'm making here. So then the concept of conditional reversible computing, that you have an operating context, a statistical operating context, that has to be generalized in the quantum domain to where you have a mixed state, which will be a probability distribution over the computational basis states of the system. And to represent the fact that we are not doing quantum computing, we have this be a block diagonal density matrix where the blocks correspond to the partition of microstates that corresponds to the definition of the computational states of the system. So this is just another way of saying that we're assuming that no coherences exist between our computational states. And so this differs from quantum computing in that we want the system to decohere to this decoherence-free subspace represented by this block diagonal structure of the matrix. And and then we have there to be coherences within a computational state, as in general, there would be coherences that exist in physical systems, like, orbitals and the molecules of the system, or qubits corresponding to like spins in the computer that aren't relevant to our classical computation. And, those can coexist with whatever these classical macrostates are that we're trying to represent. And Carper will talk about that, that modeling perspective a little more in his talk. So then, we can define computation in terms of, some computational operation that's being performed and one of these quantum statistical operating contexts. And that's fine. And then we can talk about what it means to perform computation physically. And so here's just a notation for that, saying that we've got some unitary dynamics that operates between these two times. And, read this symbol as saying it implements this particular abstract computation defined by the computational operation, and that holds for this particular initial statistical operating context. And we can, define in detail what this means formally. And it's, there's no need really to read all this. The bottom line is just to say that the, inherent quantum dynamics of the system carries out the same stochastic map on the probability distribution over the computational states as is specified by this computational operation. And so this is just a way of saying that we will get the desired probability distribution over the final computational states, and so that we've correctly carried out the desired computational operation. And if small coherences arise temporarily, that can be fine as long as they appear quickly. Remember, since we're not trying to do quantum computing, we actually like for our system to be decoherent so that it will remain in a well-defined computational state, classical computational state. Okay, so that's enough about that. Earlier I mentioned this problem of determining if lower limits on dissipation for performing classical reversible operations at a given speed. And there aren't very many papers that address this in depth, but one early one was by Likarev, where he was analyzing limits of dissipation for his Josephson junction-based superconducting circuit, which he called the parametric quantron. And essentially the limits on dissipation here arise from the fact that errors can occur due to the system jumping over the energy barrier and getting into the incorrect state. And there are two lower bounds that he derives on dissipation, and one comes from classical thermal excitation over the barrier, and you get an expression like this, and the other comes from quantum mechanical tunneling through the barrier. All right, and both of these limits seem to have this characteristic that they scale down inversely to the time taken for the operation. But in this paper, Likarev admits that he's making some assumptions with this whole the whole framework that he used to derive these results. So he's assuming that we're essentially transforming the system adiabatic at all times in a sort of quasi-static state. And so this analysis does not include systems that have a dynamics where they're not at all times in a close to equilibrium state, but maybe evolving unitarily or under their own momentum, as another way of thinking about it, between states. So this framework does not capture ballistic mechanisms for computing. So if this is not a sort of a universal analysis. So that's interesting to note. And it's also, the exact terms here are somewhat specific to the superconducting context, although one could argue similar terms will exist for any adiabatic scheme for reversible computing using classical adiabatic transformations. Another attempt to address limits was some work by Feynman in his lectures for his course on computing and the laws of physics that he taught at Caltech in the 80s. This was during the period that Feynman was interacting with Fredkin and Bennett and other people who were interested in reversible computing. And Feynman's analysis is not very detailed. It's kind of hand wavy, but it's based on systems that are driven stochastically, via Brownian motion, so to speak, such as chemical systems, like the Bennett had considered the problem of DNA transcription, right, and described that as an example of a reversible computation that is driven by chemical potentials. And so for that case, Feynman argues for an expression like this general form, where the energy dissipation, kind of depends on the ratio between the actual speed and maximum speed. And so that's the classic adiabatic scaling relation. And then he he tries to extend that to the ballistic case, but the argument in this part of the um, lecture is very, very hand wavy. There's basically no formal detail, and so there's a lot of things he doesn't consider, and so I would argue that one could hardly say that he has done sort of a definitive analysis of the ballistic case, and that really the work still needs to be done to determine the limits of dissipation in a general formal framework. All right. So just to wrap up here, just some statements about key questions and needs for the physics of reversible computing looking ahead. We'd like to know if one can formally derive from fundamental theory lower bounds on energy dissipation of reversible operations as a function of some kind of interesting general parameters, such as the speed of the operation, or the physical size of the device, or the operating temperature, or perhaps some kind of fundamental materials properties, anything of that nature. So are there some simple bounds that could be derived? And then we might gain insight from constructing systems that actually saturate those bounds. And one question that's interesting is, are there exotic phenomena or special materials properties that could be harnessed or that might need to be harnessed in order to saturate the ultimate bounds, whatever they are? And there's some things like pointer states or decoherence-free subspaces that I think will almost certainly end up being essential. There's some other things that might help, such as topological invariance. So in superconducting circuits, we have what could be considered a topological constraint when you have a flux quantum winding in a certain direction in a bounded planar superconducting circuit. Then there's a Meissner effect constraint that prevents the sign of that fluxon from changing. Some other speculations are that one could harness some form of quantum Zeno effect, sort of a version of that applies to a dynamically changing system that would keep it locked into subsets of states corresponding to the computational states that we want to represent. So I think that people just barely begun thinking about how to answer this, and it's a very fundamental question. And so I'd love to see more work on this going forwards. Okay, quickly. Let's talk about dissipation delay products and current technology. So this is some data from the International Roadmap on Devices and Systems from a few years back, but I don't think it's changed too much since then. And it is showing that, if you plot energy dissipation for conventional irreversible computing against the delay for a logic gate, you find that the product of those is decreasing by about a factor of 10 between present day, or this is a few years ago now, and the end of the roadmap, which is in the early 2030s. And this is consistent with my discussion from earlier. Even if you assume you can get a little ways beyond this, you're still at a level of about 500 EV per bit. And that's consistent with saying that you need about a 1 EV energy on the gate electrode itself, if you account for typical overhead factors. And so this is probably, maybe one order of magnitude beyond this point is probably the ultimate limit for CMOS, even if it's refined dramatically. Superconducting circuits apparently can do better. So the simulation analysis that was done by the Yokohama group, showing that their reversible superconducting technology in theory can have a dissipation delay product several orders of magnitude below that of even end of roadmap CMOS, and even if you make a conservative estimate of cooling overheads, it still comes out somewhat better. So, you know, if CMOS does better than predicted, maybe these would be about on a par, but it's still very interesting that this very new technology is already doing better, at least in simulation, than even end of roadmap CMOS. So, you know, this all raises the question, could you do even better with some other reversible technology that has yet to be developed? And we have one project at Sandia that's exploring one possible avenue towards that. We'll talk about a little more tomorrow. But anyway, it's an interesting question. And this I won't spend any time on because we have a whole guest speaker on that, Dr. Pittaparthi, and he's going to talk about this apparent result that you can actually get exponential scaling of dissipation with speed in certain quantum systems. And so this is very attractive because it would mean there's no practical lower bound on dissipation delay product. And that would have extremely significant practical benefits if you can actually realize this in a complete engineered system. But I'll let him talk about that. And another topic that I don't have time to go into, although our collaborator is here who helped produce this result, is that, okay, there's a theoretical set of techniques called shortcuts to adiabaticity that in principle can yield exactly zero dissipation even at finite speeds. And again, there's a question about, you know, will engineering implementations be able to actually realize this or at least approximate it? But here, David has analyzed the probability of occupancy for ground and excited states of a two-level system with a missed level crossing. And if you apply these certain counter-adiabatic perturbations to the time-dependent Hamiltonian of the system, you can arrange for the excited state probability to be exactly zero after the transition, meaning that there's been no excitation of the high energy state, and the system is still in its ground state, and therefore there's no dissipation resulting from that transition. So it's quite interesting, but you know, I think more work will need to be done to see how practical that can be. And then Karpur has a talk about his approach to analyzing fundamental limits of reversible computing, which kind of expands on this decoherence-free subspace perspective. And so I won't say anything else here. I'll leave that to his talk to address, describe his plan for that. So to conclude this part of the talk, I would say it's irrefutable that for general digital computing, that if we want to get beyond you know, some very firm barriers from thermodynamics to the possible efficiency of that, then we have to move to the reversible computing paradigm. You know, there have been some critiques of Landauer's principle and reversible computing over the years, but in my view, those critiques just arise from basic conceptual misunderstandings of what is really meant by these concepts, which, you know, I think that gradually over time, you know, the critics are coming to, you know, acknowledge